Before we get started, a little recap on coordinate transforms from the first course of this Coursera specialization. We introduced you to the idea of transforming one coordinate system into another. In this case, I have a world coordinate system indicated with W and a robot coordinate system indicated with R, which is rotated by an angle alpha. We introduced the notion of using projections of one coordinate axis on all the other coordinate axes and constructing a rotation matrix from that. Here, the idea was that the dot product between two vectors is really the cosine of the angle between them times their length. Now, in a coordinate system, the length of the vectors is always 1, so this length is 1 here, and it leaves the vector between the two vectors. Now, if we look at the entries of this matrix, we first look at the x-axis of the robot coordinate system, and we take dot product with the x-axis of the world coordinate system. The angle between the two is alpha, so the entry is cosine of alpha. We then look at the x-axis of the coordinate system of the robot coordinate system again, and take the dot product with the y-axis of the world coordinate system, which is this one. What is the angle here? Well, it's 90 minus alpha. So we put cosine of 90 minus alpha here. Finally, we do the same thing for the robot x-axis with the z-axis, and that angle is always 90 degrees because the coordinate systems are not tilted against each other, so we put cosine of 90. And so you can really always do this with the cosine. It's just once you use the cofunction identities, you can write the familiar rotation matrix around the z-axis, which is cosine of alpha and sine of alpha here. And then we solve cosine of 90 degrees to be 0, 0, and 0, and cosine of 0 to be 1. All right. We then talked about how to combine rotations and translations, and the idea was if I have something that happens in the robot's frame, like the robot moves by a distance here, q, then this is given by the rotation of its wheels, but I want to know what this distance looks like in the world. So here it is just a translation along the robot's x-axis. In the world, it is a little bit along the x-axis and a little bit along the y-axis. Now we do this coordinate transformation using the rotation matrix, but then we still have to add the vector that goes from the center of one coordinate system to the center of the other. So the complete expression is I first rotate the vector that expressed in the coordinate system B into the coordinate system A using a rotation matrix, and then I add a vector in the coordinate system A. We have then executed this into doing full odometry for a differential wheel robot, in which we compute the translation delta x and we turn it into motions in the world delta x, delta y, delta z by performing the rotation. But then we also added the current position of the robot, thereby translating these little motions into world coordinates. We will now talk about rangefinders and the concept of homogeneous transforms, taking the coordinate transforms that I just showed you to an even better use case. So a laser scanner is historically a mechanical device where a mirror spins and directs a laser to measure distances to points in the environment. And you see that here the laser goes around, then it is inside the case, then it goes out again, and whenever it hits something, it jots down a point. So here you see an obstacle, like the cylinder is a collection of 3 or 4 points here, and for that you're missing those 4 points down below. So a sensor like this gives you an array of ranges as well as an array of angles, and these angles are often implicit. You have to compute this angle array yourself, because the manufacturer tells you how many of these rays there are and at which angle they start and at which angle they end. The mathematical representation for such data is known as polar coordinates. The idea is to have two numbers, a distance and an angle, and I can very easily map this into Cartesian coordinates by just looking at the cosine of this angle times the distance. That gets me the x component, and the sine of this angle times the distance, which gives me the y component. So with this I have these simple expressions for x and y given r and phi in polar coordinates. Now, for example, in the laser scanner, I can do this and I get a point cloud. Now, if you look at this example here, you will see a bunch of random points, and it might take some time to see where they what they correspond to in the environment. And when you look at this for some time, you will see this diagonal here is this box, then you see the honey jar, and then to the left you see the box here. And the reason for this is because the robot looks down its own x-axis. Therefore, the x-axis, which is here, is always at the bottom, is going this way, and the whole thing is rotated by 90 degrees, much like the robot is rotated 90 degrees in the world coordinate frame. So here you see this in a close-up, and there's a video on Coursera which explains all of this, including the code to get this data out of your robot and creating a drawing like this in detail. Now, what is the rotation matrix to turn the laser scan into world coordinates? It is, of course, of that format that we introduced in the first course of this specialization, and it consists of all these projections or dot products. So when we look at this again, we can look at the x-axis of the robot frame and the x-axis of the world frame. What's the angle in between them? It's the angle alpha, or 90 degrees, so we put cosine of alpha here. What's the angle between xr and yr? In this case it's 0 degrees, but it's 90 minus alpha. And when we keep doing this, we come up with the same equation that we've been showing initially, which is this one, and which then simplifies to the well-known rotation around the z-axis. Now, again, there's another video on Coursera which shows you how to do this, and this is the result. You will get a representation which is now in the world coordinates. And you see now the laser is very useful in getting you some kind of map of the environment. It gives you a point cloud. You can then put that on Cartesian coordinates, and you can really map out your items. If the robot moves, you will see these missing points, and eventually you might get all of the points that make up your environment. Now, there is a better way to do these coordinate transformations that you have now played with a lot with the laser scanner, assuming you watched the detailed videos on Coursera later. Instead of writing this complicated combination of rotating and then translating, we can also express this transformation as a single matrix multiplication. So what I've done here is I created a 4x4 matrix, and I multiply a 4x1 vector on. And what I get is a 4x1 vector that consists of the 3 points that I'm looking for and a dummy vector 1. Now this dummy number 1 here doesn't do anything. It really only helps us to sort of be clear here. If this is a 3x3 matrix and this is a 3x1 matrix, then you would have something like a 3x4 matrix. So this has to be a 4x1 matrix in order to compute. But now the result will be what? A 3x4, and this is 4x1, so this will be 3x1. And this might work, but then you cannot use this point in any follow-up computations. So in order for creating a matrix multiplication that works out, we create a 4x4 matrix and we multiply it with 4x1 vectors, and so the result is a 4x1 vector which we can then use in a follow-up transformation. When we want to invert this, we cannot take simply the transpose as we could do for the rotation matrix, but we can use a simple trick. We can plug in the transpose of the rotation matrix here, and then we just invert the point with the transpose of the rotation matrix, again the negative of it, and then the result is the inverse of this transformation matrix. What that means is you don't have to compute this inverse ever. You can easily construct it by computing the transposes, which is very simple, and then plugging it into a matrix form of that nature. Now I worked all these things out so you can actually see how these relate. If I go and look at this row here and multiply it with this column, I do get cosine of alpha times q of x minus sine of alpha times q of y times 0 this. And then I have to still add this p of x. Now if I look what happens here, cosine of alpha times this minus sine of alpha times that times plus 0 times that. And then I say plus 1 times this. So you see how this row is equivalent to that row, and so it goes for the other rows. The last row is just taking 0 times all of these entries and then 1 times the 1 in order to create the dummy one that we need. The whole thing also works in 2D. Very often you don't need the Z component if you're working with a robot that drives on a table. In this case, I have a 2x2 rotation matrix, but because I need that additional dimension, I add the dummy one to that, and I end up with a 3x3 transformation matrix and 3x1 vectors, of which I only use the first numbers. So now, what is the deal? Why do we need this? Let's consider this pipeline of dealing with laser data. When we read the laser data, we get an array of 360 values. So it's an R in R360. This might look confusing, but just think about a vector in 3D, which is an R3. Now we have a vector with 360 entries, so it's an R360. And we get a vector I call A, that contains 360 different angles. So for each ray, we get one distinct angle. Now what we need to do first is we need to multiply each of these values in the range vector with a value in the distance, in the angle vector. And what we need to do is an element-wise multiplication, which is just star in Python. And I wrote it down using this symbol here, which means element-wise multiplication. And I now get a vector that has 3 rows and 360 columns and contains all of the x and y coordinates of my point cloud. I now can take this vector and just run it through my 3x3 transformation matrix. And so you see 3x3 times something that is 3 times 360 will get me again a 3 times 360 array. Now you see how powerful the homogeneous transforms are, because I can very easily write this down without getting confused and probably forgetting a value here or there, but I get very clean math and I get very clean code. From now on, you will very often just see the transformations matrix symbol, which indicates the source coordinate system at the bottom and the goal coordinate system at the top. And I can then plug in these column vectors with all my data, and it will transform all of them in one operation. Now we can do a little excursus into 3D rangefinders, because they have become a very important sensor in robotics. They are also known as depth camera. There's a demo in Robotics that you can run through. It's the rangefinder demo in the guided tour. And what you will find in practice is that there are 2 different ways of doing polar coordinates in 3D. One is the spherical projection, the other one is the cylindrical projection. They now provide you with a range and 2 angles. The details of this usually don't matter, because what you usually end up with is some kind of point cloud, this time consisting of 3 coordinates that give you the coordinate of where each of these lasers or depth image sensors hit. And the reason I had to correct myself here is because there are many different technologies. It could be a laser that scans, it could be a time of flight array sensor, or array of time of flight sensors, it could be a stereo camera, and many more. And I will now show you 3 different ones. There's also a quiz on Coursera that helps you look at these in practice and read the data sheets. The first one is the Intel RealSense. It's something that provides something that's called RGB plus depth. And RGB means a color image, red, green, and blue. But then it gives you a second image, which is the depth of each of these pixels. And what you can do with that is you can turn this into a colored point cloud. We also call those voxels. And voxels are 3D points which have a 3D extension. And you can now draw this scenario here using these voxels, and you see only the front-facing parts of the elements here. And this sensor in this case doesn't range very far, so it has a hard time seeing this cup which is in the background. What you also see here is the coordinate system of where the camera is actually mounted. So the x-axis is facing down and the depth is usually in the z dimension. So you see this very nicely here because you are already used to the z axis always being blue. Another sensor is a LiDAR, the Velodyne PAC, which has 16 spinning lasers inside. And here's a little video from their website. It's a company from Pennsylvania, a spin-off of UPenn, Grasp Lab, and they do mine exploration with this. And here the color, I'm not really sure what it means, but you can usually visualize your voxel point cloud in different ways. And in this case, this might be the surface normals that are changing the color. The last sensor is radar, which became very important for autonomous driving. Tesla is now using radar sensors like this, and you can watch a YouTube video of this. So this is from the website of this company. You see the car driving, and it creates a 3D occupancy grid, as they call it. It's something we will learn later in this course. And in this case, it puts voxels down where it believes obstacles to be. You see there's also a lot of noise, so the sensor gives a lot of false readings, but then it does a good job at seeing this bicyclist here moving past the car, and it can really help the car to see things a camera cannot see, in particular when it rains or it's foggy or it snows. So the idea really is to merge this information with other sensors that you have available and add another layer of security to your autonomous drive. So in summary, range data in 2D, like a basic laser scanner, on 3D is really critical for navigation because it is the critical sensor to provide us with mapping information. You usually get range from these sensors that you have to turn into a point cloud using some geometry that is depending on the way the sensor is providing this data. We have been doing this together for the laser scanner, but from there it is very simple to do it for other sensors. We also introduced the homogeneous transforms, which allows you to write down coordinate transformations in a much simpler notation, but also to implement them much faster in a computer. And finally, you've seen a large variety of 2D and 3D range sensors. What you need to do now is go through the different videos on Coursera that explain you how to use the rangefinder in Robots, how to transform 1D range images into world coordinates, that is point clouds in the world space, and finally understand the concept of homogeneous transforms. There are always little quizzes with each of these where you have to work hands-on, step by step, and follow the instructions to see what's going on with the sensor. There also is an honor section where you can explore datasheets of the ranging devices we have just seen and answer some basic questions to validate your understanding.